Hey everyone, welcome back. We're working on continuing with our linear equation stuff. Um, we're going to kind of review what we did a little bit on Friday with the graphing from a table. We're going to show you how that works with a linear equation rather than a function. And then we're going to kind of build on that going forward with you guys kind of working on some problems to get that through. So, linear equations. What the linear equations are they're functions or equations that have two variables in them. So they're going to have an x and a y, and that's why the solutions always have an x and a y coordinate as we go through and solve them. The equations generate more than one pair of solutions, so we're going to end up with an infinite amount of solutions as we go through these. And graphing enough pairs of solutions creates a line, which is how they come to be known as a linear equation. So as we're kind of going through this, we're definitely going to want to be graphing points and then connecting all those points on our coordinate grid with a straight line to show you all the possible solutions that satisfy the equation. Like, we're going to focus on the whole number ones. We're going to focus on the ones of the twos and threes. But know that with linear equations, you can end up having an answer that's like 1.5 and 2.5. We could end up with fractional answers that do still satisfy the solution, but create the line and help us create the line. So, linear equations is the solution of an equation in two variables, x and y, is an ordered pair. So we're always going to have an x and y coordinate. And then when we those x and y coordinates are going to produce a true statement when the values of x and y are substituted into our equation. So you're going to be given an equation and asked sometimes, is this a possible solution? And all you're going to do is you're going to plug those values in for x and y and see if the two sides equal. And because there is more than one solution, the graph of the solutions are connected with a line, which is how they become linear equations. So here's our example talking about, are these solutions to our equation? Our equation is 3x minus y equals 7. They gave us 4 possible choices as possible solutions to that equation, and all we're going to do to find out which one works is we're just going to plug them all in and see if the statements are true. So you take our first one, 3, 4. We're going to have 3x, whoops, sorry. Always forget to turn on my pen. Here we go. So we have 3x minus y equals 7. So 3 and 4, we're going to do 3 times 3 minus 4 equals 7. We've plugged in our x and our y coordinate. So I have 9 minus 4 equals 7, but I'm left with 4. Taking ahead. Sorry about that. 4, so we end up with 5. That does not equal 7. So what that tells me is A is not a solution. You just do this for all of these. 3 times 1 minus, and then make sure you're being careful with your signs. It's minus negative 4 equals 7. So this becomes 3 plus 4. That does equal 7. So this may be a possible answer. What I always do is I always check them all just to make sure it's not one of these ones where there's more than one solution, because there's more than one possible solution for this equation. So that's our second one. Let's do our third one over here. 3 times 5 minus negative 3 equals 7. This becomes 15 plus 3. And we know that that does not equal 7 because it's already over 7, or we're adding 3 to it. And then our last one is 3 times negative 1 minus negative 2 equals 7. This becomes negative 3 plus 2. That does not equal 7. So our only answer there in that instance is B. So they gave us one where there's only one possible answer. And that's all we're doing for problems like these. Is it a solution? Plug it in your equation. Find out if it works. If it makes it true, the left side has to be equal to the right side when all is said and done. If it's a solution, yes, it's a solution. If it's not, no, it isn't. And that's all you're doing for these types of problems. So here's 2 examples, or actually 3 examples for you. Take a few minutes, work through them, find out which ones are solutions, enter your answers in the Edpuzzle, and come back and check your work. Okay, so what we should have gotten here. The first one, the only possible solution for that equation is B, negative 2, 10. We plug it all in, we get negative 12 plus 30 equals 18. 30 minus 12 is 18, that works. Everything else was not a solution. The second one, there ended up being two solutions for you to pick, A and C. When you did the math through, you ended up with 20 minus 21 equals negative 1, and 48 minus 49 equals negative 1. The other two possible answers didn't work. They all came out to be positive 1, which doesn't work. And then another way we ask that is another way we can ask this is the last one is determine if this is a solution. So all you're doing is you're plugging the 3 and the 2 in for x and y. So we have 4 times 3 plus 5 times 2 equals negative 22. We find out that that's 12 plus 10, so it's 22, but that does not equal negative 22, so our answer is not a solution. Does that make sense to everyone? I know it seems relatively simple, but it's part of what the linear equation stuff is. We're building up to eventually trying to get these things all sorted out and figure out what the answers are just by graphing them and doing some other math. So I want to work on graphing them all and understanding that there are multiple solutions to each possible answer or equation. Okay. So we get back into graphing linear equations. The one way to do it is like we did on Friday. It's creating a table and then graphing those points of the table. So Friday, we just kind of graphed the points and left them. We just left the points. Here we go that extra step now where we're dealing with linear equations. We're going to end up connecting all the points with a straight line. So when we have it, you're just going to do the same thing. You're going to create a table. We're going to have our x value and our y value. It's a couple of steps. We're going to use the same numbers we always do. Negative 2, negative 1, 0, 1, and 2. It's always easiest to use those 5 points because you just want to get used to using 5 points. We're going to get to a point where we don't need to create the tables anymore, but I want you to understand how we're doing it this way. So when we create our point, we plug in negative 2 for our x value. So I end up negative 2 times negative 2 plus y equals negative 3. This is 4 plus y equals negative 3. So y is going to equal negative 7. Math we have to do for all of these. So I end up with 2 negative 7. Same thing, we get negative 1, negative 2 times negative 1 plus y equals negative 3. This becomes positive 2 plus y equals negative 3. So y is going to equal negative 5. So we have negative 5 here. Plug in 0, the x goes away, so we end up with y equals negative 3. Easy one to graph. We plug 1 in, we get negative 2 plus y equals negative 3, so y has to be negative 1. And then the next one we have negative 4 plus y equals negative 3, so here y has to be 1. Kind of stop doing the math out, just did it all in our heads. You can do it that way. Awesome. Use a calculator is even better. So now what we're going to do is we're going to plug those answers into our graph. So our coordinate points are 2 comma negative 7. So I have negative 2. So I go over negative 2. I go down to 7, negative 7. 2, 3, 4, 5, 6. So there's 2 negative 7. I hate that this always does that. 2 negative 7 right there. Then I get negative 1, 5. Negative 1, negative 5, sorry. I have 0, negative 3. So here we're on the y-axis, negative 3. I have 1 and negative 1. And then I have 2 and 1. So those are my 5 points that I've determined in our table. And now all we're doing, linear equations is what we're working with. So now we just create a line. And we connect all our dots with as straight a line as possible. We're going to want to be using straight lines on tests and stuff to make it more accurate. Eventually, we're going to need to have straight lines because we're going to be needing to see where points cross to make sure everything works out so that we see what we got going on. But there we go. There's our straight line. And it's a straight line because any possible place where we cross a point, a coordinate point, is going to satisfy our equation. Let me change colors here for a minute. I'm going to put a point here. We have this point right there. It crosses our line at an XY coordinate. So if I kind of see what our coordinate is, it's 1, 2, 3, 4, 5, 6, 7. So X is 7. Sorry about that. Just to show you that this all works out, that there are multiple possible answers. And then my y value here is 1, 2, 3, 4, 5, 6, 7, 8, 11. So my answer there is 7, 11, and I plug it into my equation. Negative 2 times 7 plus 11 equals negative 3. This should work. I have negative 14 plus 11 equals negative 3. This side becomes negative 3. So negative 3. So we graphed 5 points, but then we have this 6-point way out here that worked. And we have infinite amount of points that are always going to work. Wherever our line crosses a coordinate point, we have a line, that point there, all these points will work all the way through our graph. And we'll make a solution. What also will work are the points in between. So if we were able to pick this point right here, that point there is 7.5, 9, 12. You'd plug it all in, and it would work out to be, and it will work out correctly that it would work, because 7.5 times negative 2 is negative 15 plus 12 is negative 3. So it works that way too. So your x and y values can be fractions, and they'll fall on the line all the way through the equation and the graph. Does that make sense to everyone, what we're working on? Because we can pick any number in the world now and plug it into that equation and get a value for our y that's going to fall on our line somewhere. Okay. Another example I kind of tucked in here at the end. If you want to plot this one too, I'm going to do my x, y coordinates. I'm going to kind of write it over here quickly. X minus 2y equals 8. So my x and my y, negative 2 is going to be negative 2, so that's going to be 3. Negative 1 is going to be some fraction. So see this one here, I'm going to have a fraction. What I want to work on here now is I'm going to change this up a little bit. And I'm going to do even numbers for my numbers here, because it's just going to be better for me in the long run trying to figure out my points. So negative 4, this is going to be 2. Negative 2, this is going to be 3. When I have 0, this is negative 4. I'm sorry, I'm doing my math all wrong. What a terrible day. Welcome to Monday. So negative 4, I got to get positive 8, so this has to be negative 6. So that becomes positive 12, so therefore, yeah, that's it. Sorry, my bad. Stupid math. Negative 2, I need to get negative 10, so this has to be negative 5. 0 is going to be negative 4. 2, I'm going to make that 2, is going to be negative 3. And then 4 again is going to be negative 2. So those are the points I need to graph for that one. Sorry about that. So now again, we're just going over to negative 4. I'm coming down to negative 6. First point. Come over to negative 2. Going up to negative 5. There's my second point. Go 0 to negative 4. There's my third point. 2 to negative 3. Fourth point. And then 4 to negative 2. There's my fifth point. And now again, we're just going to connect our dots as straight as we can make them without a ruler here on the board. And there we have our graph. So we've graphed 2 lines on this equation. And there we go. That's all you're doing is just creating the tables, plotting the graphs. Does that make sense to everyone? Okay. Here's 2 for you to work on. Again, create a table, plug the points into the graph, and then connect them all to the dotted line, because we're working with 2 linear equations now. We're dealing with linear equations, so we're going to be graphing lines. Come back and check to see how you did. Okay, so here's what we should have had. Your red line, the red table, works out to be the points are negative 2, negative 2, negative 1, negative 1, 0, 0, 1, 1, 2, 2. That's the red line. The other equation is our blue line. And it should work out that those are the points you had, and that's what the line should look like. It's a fairly steep line. raising from left to right. Does that make sense to everybody? Again, it's stuff we've done before. It's stuff you did on Friday with tables, just plotting points. Here we're doing something a little more in depth. Okay, so there are two special types of linear equations we need to talk about. The generic forms of them are y equals b and x equals a. We'll talk about them a little more later on. I just want to kind of introduce them to you today so you can see what they are. So when we look at them, y equals 6. We're trying to create a table for y equals 6, and we're looking to plug in x values to get our y, but we see in our equation we don't have an x value anywhere in the equation. So what happens in these instances when we look at this is we're just going to go up on the y-axis where it's 6. It's right here. That's the y-axis where it's 6. And basically what we're seeing is for any value we plug in for x, we're going to get a 6. So if we plug in 1, it's 6. If we plug in 2, it's 6. There's really nowhere to plug it in. So what we end up with here is our linear equation is basically a flat line across the graph and cuts through the y-intercept at 6, or the y-axis at the point 0, 6. So what do you think about the a-axis now? What's going to happen here? Here we have x equals 4. Same thing, there's no y value, so we're going to plug in 4. We're going to get any possible numbers of y. So here we're going to start at 4. So we put our dot at the x-axis at 4, and it's the same thing here. We're going to have a vertical line where x is 4. So it's just a vertical line that goes through the point 0, 4. So those are the two special cases. If it's y equals a number, it's a horizontal line at that number. And it's always going to be a function because it satisfies our function rule that there's only one value of y for every value of x. It's the same value for y, but there's only one value for y. X equals a is always a vertical line on the x-axis, but this is not a function because there's only one value of x, but we can have every value of y. So that is not a function when you start talking about are they functions or not. So those are the two the two special types of linear equations, the horizontal and the vertical line. We'll talk about them a little more later on in this unit. Okay, we can also do word problems with these, trying to create graphs and tables and stuff with the word problems. What this does is this kind of simplifies down our domain and ranges for our equations and our functions. Because if you looked at the linear equations, the lines go on forever in either direction. So our range and domain are basically positive to negative infinity. When you start working with word problems, though, the domains and ranges are specified because you start getting into the point where you may not be able to have negative values for x or the y. So here's our example here. The distance in miles that a runner travels is given by the function d equals 6t. Now we've been used to working with y's and x's, but we're going to start having some different equations and functions that are given in different measurements, but they're specifying exactly what the measurements are. So here we have d as miles, so it's a distance. And then we have t as time, it's a specific amount of time. So our functions, we're just going to use d's and t's rather than x's and y's to make it a little easier. But you have to remember that the number that's on the left side of the equal sign, that is always the y value. We can kind of think of it that way. So if I kind of rewrite my equation here, d equals 6t, we think of this as the y, and t is the x when we plot it out. Does that make sense? Okay. So they say the runner plans to go for a run for an hour and a half, so 1.5 hours. So again, we're going to kind of plug in and create a table. But our table is a little specific because we're going to start with t as our x value and distance is our y value. So every value of t, we're just going to multiply it by 6. We're only going to go up to 1.5 hours. So I'm going to do 1, and I'm going to do 0.5, and then I'll do 0. So if we've had no time's elapsed, we've run 0 miles. We've run a half hour, we multiply 6 by 0.5, or 1 half, we get 3. So 0.5 is 3 hours. If he runs for an hour, he's run 6 miles. If he's run an hour and a half, he's run 9 miles. Does that make sense? And then if he continues on running, he's going to run some multiple of 6 all the way out. So now to graph our equation, we just kind of go, we start off 0, 0. I'm going to go 1 to 6, 1, 2, 3, 4, 5, here's 6. That's my first mile. The thing is here, I'm going to have a point there in the middle and a point here in the middle because I don't have halves on, actually let's do this. Let's recreate this a little bit. We're going to increase the scale a little. This is 1/2. This is 1. This is 1 and 1/2. That's 2. That's 3. That's 4. Okay. So now when I graph my things, I start off at 0, 0. At 1/2, I've gone 3 miles. At 1 mile, 1 hour, I've gone 6 miles. At 1.5 hours, I've gone 9 miles. So this is our linear equation. It's a linear equation, so we can connect the dots. And off we go that way. So that's what our graph would look like. It starts at 0, 0, and it goes on positively. The more he runs, the longer he's going to, the more hours he runs, the more distance he's going to run. So when we try to identify the domain and range, remember domain is all the possible values for x. So in our example, domain has to be, or t, let's call it, sorry. The domain has, for t, has to be greater than 0, greater than or equal to 0, because nobody's figured out how to go back in time yet. So we can't have negative time. Does that make sense? Okay. And then the distance, so our range is our distance value. That's the y. Remember, it's all the possible values for what our y would be. So again, this is the range. So d, again, we didn't run negative time, so we're not going to have negative distance. So d is going to be greater than or equal to 0 as well. So you may be asked to identify domains and ranges as we go through. That's what you're looking to do. Does that make sense to everyone? Okay. Here's an example for you to work through. Again, you're going to create a table, you're going to graph the points, and then you're going to determine what the domains and ranges are to kind of come down with what we're looking at. Okay, so here's what your graph should look like. It's a little different than the last one because we're not continuing on. We're planning on pumping $10 worth of gas. So that's going to have a finite end to our stuff. So the table should be 0, 0, 1 and then 2, 2 and then 4, 3 and 6, 4 and 8, and then 5 and 10, because that's what the G is. We're just kind of solving it backwards. So if we're going to pump $10 worth of gas, that's our C value. We're going to get 5 gallons because it's $2 per gallon. So we start to think of domain and range here. Our domain for this one is really G again, because G is the gallons, the X domain, the X value is G. G is going to be less than or equal to 10 in our equation. Does that make sense? Because we can go from 0 to 10. We can't go lower than 0. Actually, it's really going to be that. So it's the domain is actually this. I'm sorry. 0 is less than or equal to G, which is less than or equal to 10. Because we can't go lower than 0 because you can't get money back for gas you pumped, or you sell back. And then our range again is our cost. Sorry, that's not 10, that should be 5. My mistake, again. This should be 5 for our range. Our cost is the dollars, so that again, that's 0 less than or equal to C, less than or equal to $10 as we look at our function. Because we have continuous. The gallons we're pumping are continuous. I don't know if you've ever pumped gas for your mom or your dad, but it's always flowing until we get to where we want to be. So it's always going to be a straight line kind of continuous thing. That's what linear equations are. They're continuous functions counting all the possible values of x for y. So does this make sense? Okay. So one last thing we're going to talk about today, and then we'll see more of it as we go forward, is pretty much all the examples we've seen today are what they call standard form. It's one of three forms linear equations can be written in. It's the standard one. It's the one that everybody uses. We'll use it a little later on, more prominently in what we're doing. But right now, just know that it's ax plus by equals c, where a and x are both coefficients that we're multiplying our x and y values by to see if we can get them to equal to c. So when we're trying to prove a true statement, we're multiplying x and y by numbers to see if they're going to equal c. The c term is always some constant term of our equation that's always going to kind of be in there, but that's what we're trying to get the equation to equal. Does that make sense to everyone? You'll see as we move forward this, we can move some stuff around to get different forms, which are a little easier to work with than standard form, but just standard form is what we need later on, where stuff gets, you can get to every other equation from that. So that's the end of today's lesson. I want you to go out now. There's a Pear Deck activity. I'm hoping it's going to work. It's kind of drawing some graphs on Google Slides. So you're going to create your tables, graph the points, and draw the lines in on the graph on your Chromebooks. I know it's probably going to be a little bit tricky, but it's something that can be done. I just want to be able to see that you can do that. And then again, there's going to be a homework activity out on edgeelastic.com, kind of covering the same thing. So it's just practice, practice, practice of graphing lines and being ready to go forward with everything that we need to know for our linear equations unit. And I will talk to everybody tomorrow.